All right, welcome to topic 10.2. In this topic, we're going to talk about how we mathematically represent concentration of a solution. You will want a calculator and periodic table to go along with this topic. So you may want to pause and go get the materials that you need to be able to work along. So concentration can be open to interpretation. So if we say the word dilute and concentrated, what does that mean? For example, if you're making, I keep going back to Kool-Aid, how I make Kool-Aid versus how somebody else makes Kool-Aid. If we're not following the instructions, I may make it kind of dilute. Somebody may make it very concentrated. The amount is, we kind of say dilute is a small amount of solute. Again, solute being what is being dissolved. Solvent is what's doing the dissolving. Concentrated means there's a large amount of solute to solvent. So, but again, that's open to interpretation as to what is small, what is large. So dilute and concentrated are not always the best terms. Again, concentration is looking at how much solute is dissolved in that amount of solvent. So what we have as chemists is we have different ways of defining concentration. I'm going to just emphasize molarity. Like I said, this is not the end all be all, but it's giving you exposure to things that you will see more in depth. Molarity is a relationship between the number of moles of solute, again, what's being dissolved, in 1 liter of solution. Okay, so molarity standardizes conversations about concentration as to what is dilute versus what is concentrated. So it doesn't matter what substance you have. If you're talking table salt and you're comparing it to a potassium nitrate salt solution, it doesn't matter what it is. If we know the molarity, we can have conversations about what is concentrated and what is weak. Okay. We have a formula then for molarity, where molarity is equal to the moles of solute over liters of solution. So a lot of times you'll see people write their formula. Molarity, we use an uppercase M. If you use a lowercase m, you are defining what's called molality, which is a formula Dr. Downs will work with on an AP Chem. So molarity is uppercase M, and a lot of times we just write mole over liter. Okay, so when we define the concentration here, we have very defined units here. The amount of something, the amount of solute, like salt, has to be in moles. How much solution we're dissolving it into has to be in liters. Okay, so I got a few examples with that. So here it says a saline solution contains 90 grams of sodium chloride per 100 milliliters of solution. What is its molarity? Okay, so as we can see in the reading here, molarity is what we're solving for. And what we know from our formula is that we should know moles and we should know liters. Well, there's a few things going on here. I know that I have 90 grams. That isn't going to work. It has to be in the unit mole. So we know that we have 0.90 grams of NaCl. So in order for this to work, we need the molar mass to allow us to complete a conversion. And I need to grab a calculator real quick. So what we're going to do is find our molar mass of sodium chloride. So sodium is 22.99 and chlorine is 35.45. So we have 58.44. I know in order for this to get from grams to moles, I need to divide by the molar mass of 58.44 and multiply by the 1 mole. So I'm going to keep 2 sig figs from my 0.9. And we get a pretty tiny number here. So we get 0.015 moles. Okay. So then here we can see our volume is 100 milliliters, which also doesn't work. We have to convert that. A liter is 1,000 milliliters. So I'm going to divide that. So then that is 0.1 liters. Okay. This only had 1 sig fig. So again, this whole thing is based on that molarity is mole over liter. So I go ahead and put in my 0.015. And my amount is 0.1 liters. So 0.015 divided by 0.1 should be 0.15. Yep. So we get 0.15. The unit here is nothing's canceling, which we can say moles per liter, but we label it as an uppercase M for molarity. So this is a 0.15 molar solution, and that's the basics to the molarity equation. Okay, so here's another variation. Here it asks how many grams of solute are present in 1.5 liters of a 0.20 molar sodium sulfate. So through here, it's asking how many grams. Okay, I get to grams through the mole. So that is what I'm solving for here. So what I have to work with is I have a volume here is 1.5 liters. And here I have my concentration of 0.2. And it's of Na2SO4, sodium sulfate. Well, the formula for molarity is equal to moles over liters. So I'm going to go ahead and plug in. My molarity is going to go on the left-hand side of 0.2 is equal to X over 1.5. So to get X by itself, I'm going to go ahead and multiply. So 0.2 times 1.5, each of those have 2 sig figs. So I can say 0.30 moles of sodium sulfate. Again, I'm not done because it's specified we don't want moles, we want grams. So we need the molar mass then of this compound. 1 mole will go in the denominator, and we're going to multiply by the molar mass. Looking at a periodic table, we have 2 sodiums. Those are each 22.99. We have sulfur, which is 32.07, and 4 oxygens, which 4 times 16 is 64. So the molar mass here is 142.05 for the whole substance. And I'm going to go ahead and multiply by my 0.3. I can keep 2 sig figs. So through rounding, not that you can see this, there we go. Maybe that's a little better. Through rounding, I would say with correct number of sig figs, X being the number of moles, or number of grams from the number of moles would be 43. Na2SO4. And that gets you through number 2. Now in number 3, it asks how many liters of a 0.75 molar magnesium sulfate solution are needed to get a 0.27 mole of magnesium sulfate. So here we're asked to find volume. We're finding liters. We know here that our concentration is 0.75, so molarity is 0.75 of the MgSO4. And we have moles, which is 0.27. So for our setup, we have that molarity again is moles over liters. I'm going to go ahead and plug in what I know. So my concentration is the 0.75 is equal to my number of moles, 0.27, over X. Again, we need to get X by itself through rearranging. So I'm going to multiply by X to get the fraction gone and X out of the denominator. So X times 0.75 is equal to 0.27 moles. So then what we know is to get X by itself, we're going to go ahead and divide. And so we're going to take 0.27 divided by 0.75. We get 0.36. And then again, to understand what our unit's going to be here is molarity stands for moles per liter. Why I bring that up is moles is what's doing the canceling, and we get a volume of liters. Doesn't ask for a different unit, so we're ready to go ahead and solve for molarity. Okay. The next thing we're going to look at is how we dilute. So a lot of times in chemistry labs, things like acids especially, we buy in these big jugs of like a liter volume, or a gallon, I should say, not a liter. So like we get these big quantities of acids, like I said, especially, and sometimes bases, where they are a solution, in this case meaning a liquid solution. We buy them concentrated. So a lot of times as chemists, we don't use the concentrated form. We water it down. Okay, so it's like we take Kool-Aid almost and water it down a little bit. So stock solutions, for example, when we buy hydrochloric acid, we buy it in bulk in a 12 molar concentration, meaning there's 12 moles of HCl per 1 liter of the HCl acid. And so oftentimes we don't work with that concentration. A lot of times we work with 1 molar, 0.1 molar, a half mole. I think the strongest I ever give you guys is a 3 molar hydrochloric acid. Sulfuric acid comes as 15 molar. That stuff is really nasty stuff. So we dilute it down. And so we have an equation that shows me and tells me how much of this concentrated acid do I need. Okay. So what we have is a formula, M1V1 is equal to M2V2, where 1 is our initial conditions, just like gas laws, and the 2's are the ending conditions. M is molarity, V is volume. Okay, so the big thing with volume here is, unlike the molarity equation, as long as your units agree, like gas laws, you don't have to have liters. So like pressure with Boyle's law could have been an ATM, unless it's specified as something specific. As long as they canceled, you were good to go. Okay, so you can leave the dilution equation in milliliters is often the other unit we see if it's not in liters. Very rarely do we talk in volume in terms of other units out there. Okay, so it asks how many milliliters. I'm going to give the bell a second to ring. It's asking how many milliliters. So we're finding volume. So volume is going to be my question mark of a 0.17 or 1.7 molar potassium nitrate solution are needed to make 510 milliliters of 0.7. Okay, so the ending conditions here is the weaker, okay, the dilute. So my volume 2, I am ending with 510 milliliters. And I want it to have a strength, a molarity of 0.7. Okay, so this is how I want it to end, and this is how much I need of it. So I know my concentrated, my stock solution that I have on my shelf has a molarity of 1.7. I want to know how much of this do I need to add to water to dilute it, to water it down. Okay, so V1 is my question mark, where I have M1V1 equals M2V2. I'm going to go ahead and plug in. So my molarity 1 is 1.70 and volume 1 is my X. I know that I want to dilute it down to 0.7 and I need 510 milliliters of it. I tried to add an extra 0 there. Mathematically, this is Boyle's law in that it's an indirect relationship. So I just got to divide here to get X by itself. And so what I'm going to go ahead and do here is take 0.7. I'm going to multiply it by 510 and divide that out by 1.7. Looks like all of them have 3 sig figs through the use of the decimal there. So this tells me that I need 210 milliliters of that concentrated. Now, to bring this up to a total of 510 milliliters, I would then fill the rest up with water. And I'll explain that more with my next example. Okay, so that's my ending answer. And it asked milliliters, so I didn't need to convert there. Okay, so in example 2, you typically know what you need diluted. You know how much you need and what strength you want it to. So what it's telling me here is I need 0.2 molar and my source is a 1 molar solution. So my ending conditions, I need 250 milliliters of the dilute, the weak, in this case lithium fluoride, and I want it at a strength of 0.2. I know that it starts out concentrated at 1 molar. And I don't know how much of this I need to be able to water down to create this strength of a solution at this amount. So again, the foundation here is that M1V1 is equal to M2V2. I'm going to go ahead and plug in my 2. So I have my molarity is 0.200, and I need 250 milliliters. My M1 is that I know it's 1 molar, and I need to know how much of this strong concentrated I need. So we're going to divide by 1. And again, that just shows the canceling of units here. So again, this is going to result in milliliters, which it doesn't specify a specific unit, like it has to be in liters. So we just have to take 0.2 times 250. And we get an answer with 2 sig figs is going to be 50 milliliters. So what it's asking us is, how would you actually make this? Okay. So the steps that you would go through is you would obtain 50 milliliters of the, and I'm going to add a decimal here to give it 2 sig figs. So we're going to obtain 50 milliliters of the concentrated, so the original stock solution. So we're going to get 50 milliliters of the 1 molar lithium fluoride. We would add it to a volumetric flask. And then we would add water to this flask until it reaches a volume of 250. And this is how you water down something that's concentrated to something that's less concentrated through the molarity dilution equation. So if you have questions, let me know. Otherwise, reach out and finish up those problems that go along with it.